seen before. And then, of course, people started pushing the boundaries of that and said, okay, what not just about noise, what if I modify the sentence in a way that I sort of expectations of how the meaning changes? So people start thinking about semantics of natural language in a bit more refined way. So if I take any sentence and I add some insult, well, I assume that the sentence is becoming progressively more negative. The sentiment of the sentence became more negative. And this would happen. Or this is another, ooh, nice. Well, no problem. It gives people to think about, I think.
By the way. That's part of the Simpósio. What's planned, right? Give an idea what it could be like, Amazon for efficient research. Sometimes we. You know? Now it's the power. I have the full experience.
Yeah.
This is robustness testing.
Robustness testing, yes. Will I give the same presentation even when the condition changes?
We'll call it a small presentation.
Well, let's call it small. The other thing you can try is insulting me and seeing if my presentation becomes more negative. But yeah, maybe I can continue a little bit without the slides, and then the slides will come in, hopefully. But yeah, what I was saying is that basically people have a lot more expectations about natural language. Not as much as with formal language, you know. We are all used to computer programs where the semantics has very well defined. In natural language, sometimes you have to deal with ambiguity or irony, sarcasm, so the same sentence in different contexts may mean two completely different things. But still, there are some expectations. And so the idea is that whatever I'm doing as a machine learning engineer, I want this system to be robust or at least predictable and conform to these expectations. And it's a hard problem because, of course, language is this sort of infinite space. You can have input sentences that as long as you want. The input text may contradict itself. You can have all these things that now people are doing with ChatGPT and saying, parts of the prompt is an instruction. I'm telling ChatGPT, do this, be creative. And part of the prompt is data. And like in computer, it's clear what is a program and what is data that the program is working on. In a prompt in ChatGPT, you are expecting the model to somehow understand it. So I'm telling the model, repeat this. So that's an instruction. And then I'm going to tell the model in the same prompt a piece of text that I want the model to repeat. And I expect the model to understand that repeat this is an instruction, and what happens after that is data. How do I enforce this? I don't. But the user expects this to happen, right? And so there is this terrible ambiguities where when we communicate between humans, we expect people to understand from context, to do all this sort of meta stuff. But with machine learning models, we don't even put it as a training objective. So we just expect that somehow the machine learning model has figured it out, which is difficult. Okay, so I think I reached the point in my slides where I need the slides, but there's no slides. So we'll need to open the discussion and we do a bit of panel.
By the way.
Oh, beautiful. Well, let's do a bit of panel. I think that's the only way that makes sense while things go back online. So do you have questions?
So far.
So far, or questions about, I don't know, anything large language model related? Otherwise, I should be like the teacher, start asking you questions.
Yeah, hi.
Yes, thank you.
So it's more about how we verify the neural network itself. So I know there is a different format for floating points to improve accuracy and the space, like the B posted 16, right? That's the one created by Facebook. Have you tried use this new floating point methodology to verify
Okay.
the neural network? And is there any difference from verification tool side, if it's better to use this coding, this big code 16 coding, or just plain floating point coding?
Yeah, okay, so the question is about different floating points encoding. So that's the second part of my talk, but we can start discussing now. So the idea is, again, the biggest problem in AI safety is not really doing the verification yet or the testing, but is trying to define what is it that we want. So in terms of how actually the hardware is executing the neural network, the problem is the data scientist, the machine learning engineer doesn't think about that. So for them is, yeah, that's the training set, I'm trained, there will be some underlying library that does the magic for me. And the way they think is in terms of approximation. So the reason why, for example, I think was NVIDIA tried to push for the floating point at 16 bits is that for them is like, I mean, this is going to introduce a little bit of error with respect to floating point 32, but it's, you know, the neural network is an approximation anyway, so who cares? So that's the problem. They have this attitude. So now when you come with the verification thing, you say, okay, if I want, you care, but then you have to tell me how you care. And the way we approach it is in terms of equivalence checking. So because the way the data scientist is doing all the tests and the training is probably on a 32-bit platform or even 64-bit, and they are sort of thinking about the problem as if it is in infinite precision. So in their mind, the neural network is running in infinite precision in this beautiful mathematical world, and now, since I know the hardware is actually not ideal, I have an equivalence problem. So is the neural network in infinite precision identical, according to some definition that you need to specify, to the neural network running on 16 bits? And again, this problem is even worse because what people do is not just 16 bits, right? They want to run in integer 8 bits, right? Because it gives you even more compression. And then how do you specify this? So if you're doing classification, for example, image classification, is your definition of equivalence, or the output class should be the same? So if I predict a dog, then you should predict a dog? Or is it an error bound? So whatever output the neural network is, the error that this approximation introduced needs to be less than 1% or something like that. And even just that choice, which seems like, okay, I mean, they're both definitions of equivalence, that choice completely changes what sort of algorithms you can use. Because if you care about an error bound, then maybe you can do some abstract interpretation, propagate errors through the neural networks. If you do classification and you just care that the output class is the same, then you have to sort of figure out where is the boundary where, like in the input space, you'll have a boundary and everything that's beyond this boundary is a dog, and as soon as you cross the line, it becomes a cat. But now, once you change your representation, instead of having a smooth line because you're infinite precision, you have some strange zigzag because it's quantized. And now you have to track where this line is. And you have to come up with an idea of, is this safe, is this not safe? So again, my point in this talk is that sometimes just defining what it means, safety, is like a big deal. And then, once you've done that, you can worry about what is the algorithm, can it scale to large neural networks, and how do you solve it?
Eduardo.
Yes?
Guys, we had a preemptive break. So this was not supposed to happen, and we couldn't prove it would happen. Although we expected, because it's the rainy season, so I'd like to ask just a 15, 20 minutes break, so then we can continue, okay? We have to change, I think, the project.
Did it blow the light?
Yeah, perhaps.
Ah.
Sorry about that.
Oh, it's okay.
I think it's better if
Good, so start the last talk of the session, and then as I mentioned before, so we are going to start at 2 p.m., right, John? Yes. Yeah, 2 p.m. With a tutorial on verification of security property.
No, it's another one. I sent it to Edward before.
So the talk that Edward is going to give is about one data set that he has created from neural net implementation, and then to show how is the state of the art in the
Called
field
neurocode
to
bench.
verify those models that was produced by this data set.
Yeah, one second, we're fetching the slides. Yeah, so this talk will be more practical. So if you're bored of listening to me, I'll try to have a different styles. I'll try to be a bit more fun before we get to the lunch break. So I'll give a little bit of introduction while the slide go in. So as I told, the machine learning people think in a very different way from us. They are stuck in a high-level mathematical world of infinite precision. Everything is beautiful, and I only care about accuracy. And then as we start doing safety, we need to worry about more and more low-level problems. Oh, there we are. Thank you. Nice. Yeah, so the machine learning people are there stuck in the world. They talk about gradient descent and things. And then in my previous talk, in my previous talk, we mentioned a little bit that sometimes there's an engineering phase where a machine learning model is compressed and changed in order to be deployed, and this may change the behavior. But I mentioned briefly that, I mean, this is not enough. You can go further down to low-level details and start wondering about the software. So all of this, for a data scientist, happens at the level of a library. It's been mentioned, PyTorch, TensorFlow, like this is like something that the data scientists use, and it just trusts that the library does things. What is the library actually doing, right? The library is code. It's a layer of software, and this software can have bugs. The software has its own behavior, and who knows what's happening there, especially a library like PyTorch is huge, right? So what's happening there? And then, of course, if we want to be very, very paranoid, we don't know what the hardware is doing, but we are not going so low level in this talk because otherwise we'll never end. Okay, so usually I put memes in my talks, so it's become a bit fun, but yeah, basically when I show this to the machine learning people, I mean, many of them are computer scientists, so they know something is happening underneath the library, but they just choose not to worry about it. But we need to worry about it. So this talk will be at this level. So we're just talking about software. We are not gonna go down to the hardware. So what happens when you look at software? And in order to convince machine learning people that it's important, I show them these results. This is a very, very niche field of machine learning where they talk about machine learning systems. And their worry is, once I go through this deployment pipeline, so from the data scientist model, I use a library, the library gets deployed maybe on a phone or on a computer, what happens? And what they say is that what happens is that depending on which platform you use, depending on which library you use, depending on which camera you use, depending on all these practical factors, the behavior of the machine learning model changes. Now, of course, machine learning people only care about accuracy. So they will run experiments where they just run, they run the same neural network on different phones and say, oh, if I use an iPhone with TensorFlow, my accuracy is 93%, but if I use an Android phone with PyTorch, then because of the camera, because of how the library is implemented, then I get lower accuracy. And this should not happen, right? As an engineering system, you want the pipeline to be transparent. So whatever happens in the deployment pipeline, you should get the same result, but you don't. And for us, it gets even more problematic. So maybe there's a very recent competition in neural network verification. And the verifiers that exist for neural networks tend to work at this abstract infinite precision level. And what happens there is that I contacted the organizer of this competition because I was trying to reproduce some of the results, some of the proofs, and I couldn't. So we have a neural network verifier that does the proof and the reasoning in infinite precision. But once you get, for example, a counterexample, and you try to just plug the counterexample inside your implementation of the machine learning model, and you read the output, it may be that the output actually does not violate the property. Actually, with some of this counterexample, sometimes the input does not fit into the precondition because implementation issues, floating point, something has been lost in translation. And this is a problem because any tool we have that sorts of work now in neural network verification gives us a proof, but then we realize, well, no, this proof depends on the actual implementation, the actual behavior of the software we are running, and so we cannot make a statement about this neural network is safe. The only statement we can make is the implementation, this very specific implementation of this neural network on this platform is safe. We lose the generality because it depends on how you implemented things. But I happen to have Lucas as a boss. So Lucas is an expert in software verification. So this is actually not a problem. This is an opportunity because we are expert in software verification. If the only thing we can do is make a statement about the safety of a piece of software, this is great. We can do that, right? So then we stop thinking even that we are verifying an AI system of a neural network is just a piece of software. So just give me a piece of software, and the fact that it's a neural network doesn't matter. It will do some loops, it will do some multiplication, it will do some additions. Just write the safety property and verify the software. So this was our plan. It sounded a reasonable plan. And it sounded a reasonable plan, especially because there is so many decades of software verification. So the tools are very mature, right? So it sounded like the sort of very quick research project that you do just as a start to see what happens. Just use existing software verifiers on neural network code. Surely they will work. But of course, in order to measure things, you need to do a benchmark, like what is the metric. And so the contribution for this workshop that we present is a benchmark. So we literally try to create a representative set of pieces of software that implement neural networks. That was our goal. And of course, we have some desiderata, right? So we would like these pieces of neural network code to be somewhat representative of what people use. We would like them to be plain C, because the majority of software verifier really like doing plain C. We would like to have a variety, so not all be super huge neural networks, have small pieces to large things. And most importantly, we would like to know in advance what is the expected verdict. So we would like to have this piece of code with a safety property and know in advance, is this safe or is this not safe? Because in this way, we can evaluate whether the software verifiers are telling us the truth. And we found that there's some nice libraries that are designed for microcontrollers that do exactly this. So you give them a neural network, maybe specified in PyTorch or TensorFlow, and are able to create some standalone C code. Because people who do microcontrollers, it's a low power, low resource platform, so they really like to have a piece of standalone, no libraries, just plain C code. I can compile it and run it on my small microcontroller. So here's the benchmark. Now I will go a little bit through the categories so you have an idea of how we built. But like any nice benchmark for software verification, you have various categories. So each category is a bit uniform, but the categories have different characteristics. And you can see it's fairly balanced in terms of how many instances are safe, how many instances are unsafe. OK, but before going that, since it's before lunch, let's play a game. OK, so all of this is in floating points. That was our decision. So all of what we've done is assuming that the computation model is 32-bit floating point. because that is the most common way of doing data science with neural networks. But again, remember that I am used to speak to machine learning people. Machine learning people are not used to think about lower level problems. And the machine learning people will say, oh, I want a function that has a shape because my neural network uses it. I don't care about the implementation as long as it has that shape. But then a programmer needs to implement. This is hidden by the library. So for example, I don't know if PyTorch or TensorFlow implements that thing in this way or that way. Mathematically, in infinite precision, they're identical. This is the definition, and this is just realizing the hyperbolic tangent with some tricks has the same shape. They should be identical, but of course, if you actually implement this and this is floating point, one thing is rescaling a floating point result, and another thing is making a division. You'll get slightly different roundings, right? So that the two things have different behavior. They are very close to each other, but they have a different behavior. And of course, the programmer writing the library will try to write the way that it's faster, maybe, or will wonder what is more precise. And then, of course, if you have floating points, so this thing is already bounded, so whatever input it is, even plus infinity, it will give you a finite result. But if instead you write a definition that it is exponential, if x, the magnitude of x becomes a bit too large, then the result of this exponential will be an infinite, right? So you lose precision. And if you implemented these things, you will have to worry about this. So now we go to the game. And then this is something machine learning engineers do to speed up things. So that's exactly the same function as before, but I don't want to call any mathematical library function because they may be slow. So they replace it with something that is cheaper to compute, because this is an if statement, and this is division. This is cheaper than calling a mathematical library. And now, well, we want to go to lunch, so let's skip to the difficult question, which is the last one. So in infinite precision, that thing is monotonically increasing. Clear, right? It never goes down. My question is this monotonically increasing? Question for you. In floating point 32 bits, I have to. Michael, what's your guess?
My idea is what happens when X is NAND.
So, yes?
This is NAND.
Good point. So let me rephrase my question. Is this monotonically increasing for finite x?
If X is in, this is 0, right?
If f is inf, you get inf divided by inf, or minus inf divided by minus inf. So yeah, you get not a number. But if x is finite. Okay, so we'll leave the question hanging. I have a slide at the end that shows you the counterexample. This thing is not monotonically increasing. You can say that if you go further down, this will be flat, so it will always be -1, so it's not increasing anymore. Yes? Aha, Vince.
So is it because of the absolute function that it's not always non-decreasing? Is it because of the absolute function? Because of the binary encoding of floats?
It is not because of the absolute function, but it is because of the floating point. So you get some weird cases where the real problem is that you have two occurrences of the same variable. So you may be dividing a number, divided, the same number is slightly different because you added 1. And at the end, I'll show you a counterexample. I'll show you now. There are some points at which this thing actually decreases. Okay, so if, that's the thing. So if you compute that thing in these numbers, so it's almost 15, you get this. And if you compute the same thing for a number that is ever so slightly larger, so x2 is slightly larger than x1, you get a number that is slightly lower. So there are some points at which that function is actually decreasing, just a tiny bit. Because, again, you're dividing 15 by 16, right? This is 15 divided by 16. And this extra thing messes up the rounding. So it decreases by, very little. So you can say, oh, it's a good approximation, right? This is 10 to minus 7. So it's not too much of a problem. But of course, if you want to do verification, right, you want to do bit precise, you want to actually verify this behavior, you have to model this. Yes?
For model checking, for data mining people, machine learning people, is that a problem at all? Because that doesn't change the shape of the...
No, so that's a problem. So for machine learning people, this is not a problem because for them it's like, I mean, it's good enough approximation. Then I will run gradient descent. So even if this approximation introduces some slight differences, then gradient descent will compensate by modifying the weights. But the problem I have is that if then you come to me and you say, I want to verify a neural network that contains this, and I verify in infinite precision, I may miss some very strange corner cases where there's actually a counterexample because roundings, right? This error they introduce here may accumulate. So these examples for me are motivation to actually do software verification where I'm actually modeling what the floating point is doing. So these small errors may actually cause unsafe behavior in some corner cases. But machine learning people just don't think about it.
Oh, okay.
Okay. Cool, so end of the fun part. Let's go back to the boring part. Okay, so what do we have in the benchmark? So the first thing is like we wanted some small things. So we decided let us write some very simple safety properties about single mathematical functions called or activation functions. So things like, oh, the exponential of x will always be greater than this, or we can invert the function and we'll get more or less the same thing. So this will give us some very small pieces of C code with maybe one definition of a function data scientists love a lot, and just some simple safety properties that just, okay, is this bounded? Is it ever negative? Things like that. And this just gives us some small pieces of code just to check that the verifiers actually are doing things. And then we have some actual neural networks. So one of them is a very old thing. I think it's from the 70s. It's an error-correcting neural network. So it's a recurrent neural network. You plug some inputs, some binary inputs, and the neural network is able, over several iterations, to correct any errors. So the way this thing is, this neural network is not even trained. Like, you know exactly what weights it should have, and is able to remember a certain number of patterns. So if you, as an input, you put one of these patterns with some mistakes, over the iteration, it will correct all mistakes and spit out the corrected pattern, which is good for us because we know what the output of this neural network is, because we know that this neural network is correcting the code. But the verifier doesn't. So the verifier is forced to actually reason about the whole behavior of the neural network, but we know what the verdict should be. So that's one of the tricks we use. The second trick is something that they use in engineering a lot. You may have a complicated function, but it's a function of just one input, one output, and you may use a neural network to approximate it from data. The advantage of functions like that, so neural networks that can be as complicated as you want, but they only have one input and one output, is that you can brute force it. So you can literally test every single possible floating point input and see what happens in the output. So in that way, you can have, we have even neural networks with like 1,000 of neurons, but we know exactly what they should be doing. But again, the software verifier might not use this sort of brute force testing strategy, may use bounded model checking or arbitrary interpretation. So the verifier now is forced to do a more complicated reasoning approach, but we know what the output should be of the reasoning. And then the other thing we did is go back to this neural network verification competition, try to find some very, very small benchmark they had, convert them code and use the verdicts after checking what it is. So we have one of these microcontroller libraries to transform it into C code, and then they come with the specification as safety properties. The only thing is we need to check whether this specification is still valid after the transformation from infinite precision to C code. So all in all, we have the benchmark that you already saw, and you can see that how we know which was safer and unsafe are a bit different. Right? And then again, for us, our job is done. We created the benchmark. Now the fun part is, are state-of-the-art software verifiers capable of actually verifying this thing? Because nobody tried before. And so we went to the software verification competition. We pick up the winners of the past edition, checked the ones that we could run with licensing properties and things like that, and we tried on a benchmark. And the results were appalling. So these 6 verifiers are basically the top scoring in the reachability category in SVComp. Not the winner, unfortunately, because we couldn't run the winner because of licensing reasons. And they use different strategies. So this has to a bounded model checker. This one is a portfolio, so just a mixture of things. U-Automizer is use automata theory. Pesco and Pinaka, I don't know which technique they use, but you have a variety of techniques. And what you can see is that there's a lot of unknowns. So there's a lot of cases where they just can't cope with the complexity of the problem, even though some of these C codes are really like 10 lines. But what is more worrying is that a lot of incorrect results, right? Which means that if anybody wants to verify a piece of neural network code and uses an off-the-shelf verifier, they cannot trust it. You can see some of them is almost like 50-50, like basically it's like tossing a coin. So these verifiers have decades of development. They've been tested in all sorts of ways. There's like big teams working on it. Why are they not performing as you would expect? And also, this was one of the comments that one of the reviewer made. Maybe the reviewer is in the room. I really appreciate this comment. Because it reflected the frustration that we also had. Because we wanted to have a small paper where we do this benchmark, we test the software verifier, it's done, and then let's move on with our life. But we couldn't. And this reviewer said, well, I mean, what's happening here? This is ESBMC saying, oh, there's 255 true ones. This is 224. Is this a problem in the software verifiers, or is this a problem in the benchmark? So maybe our benchmark is messed up. And so we did some analysis and say, well, OK, so one thing that seems to be is that most software verifiers, they don't really have a correct semantics for mathematical functions. So as soon as I call, let's say, an exponential, they just don't know what it does. And so they will just return whatever. And of course, it will create a lot of false counterexamples, right? Once you have some important pieces that returns anything, you'll have false counterexamples. The unknown, you can say, OK, maybe it's because the neural networks are too large, so it's just too large of a program. But maybe there's other bugs. Maybe just the fact that we are running these software verifiers on something that usually is not run on is just triggering some hidden bugs. Right, and so when we submitted this paper, which was, the deadline was the 1st of September, so a few months ago, this was future work. So we really need to reproduce this, because it's such an incoherent experimental result. What do we do? And the only idea we had is like, well, let's submit this benchmark into SVComp. Because then we have two things. First of all, we will not be running the experiments. They will be running the experiments. So if we messed up the experimental setup, now we have confirmation. And second, like the authors of this tool have a chance to look into this and see what happened. And then, of course, at the time, so I prepared these slides a while ago. We say, OK, maybe we need to do something about the semantics of the mathematical library, etc. But I think today is interesting because in the past weeks, we actually managed to do this. So this is stuff that you will not see in the paper. So this is where we were at. This was run on the 24th of August, before paper submission. And this is the pre-runs of the current edition of SPComp. We don't have the final runs. Like I did this last week. So this is still a mixture of pre-runs run with different settings. So the numbers may change a little bit. But what is interesting to me is that what we wanted actually happened. So the authors of each tool had a chance to look into what was going wrong. And so first of all, you see most of them are different tools because, as I said, we don't have the final runs yet. But some of them are the same. So you can see SBMC, you can see CPA Checker, you can see PESCO and U-Atomizer, so some of them correspond. What you can see at a glance is that the number of incorrects has dropped. So now there's almost no incorrect results. But also the number of correct has dropped. So what is happening?
It's because of the time, to be fair. Because this is run with 90 seconds and the other one was 900.
Yes, but I have another thing, which is a lot of these correct results are not results. So
They are guesses.
they are guesses, exactly. So if you guess, if you always guess true, let's say you have a tool that has a bug and that makes it always guess true, 50% of the time you'll be right, 50% of the time you'll be wrong. So you have a lot of incorrect and a lot of correct ones. So for example, in SBMC, so this is our tool, so we know this was happening sometimes. And so you can compare now to what is happening here. So we fixed a lot of bugs. So now we don't have any more incorrects, but it means that a lot of our guesses have disappeared as well. So in a sense, okay, now the tools are correct, so they are not lying anymore, but they are not solving the benchmark. So remember, this is almost 700 benchmarks, and the best tools has only 22 corrects. Yeah, maybe with a longer timeout, they solve a few more. Yes?
Yeah, so this is slightly disturbing, this discussion. So I would like to understand a bit better the concept of soundness that these tools are ensuring. If you go back to the previous slide. No, the previous one, actually. Yes, that one. So when you had the preliminary analysis there, and you say no support of mathematical libraries, what you described was what happens when you do not consider the correct semantics of something, so you approximate it.
Yeah.
So in this case, generally, verifiers in general, they will give false positives, where they would produce a model that is not actually a model, and then you would rely on the tool using that to check that the model is correct. That, however, should not impact the incorrect results, in the sense that if you show that there is no possible way to have a model, that is the case in whatever way you have interpreted that symbol. So I would expect to be unsound in the sense of giving false positives, but not to be unsound in the sense of giving false negatives.
Yes, so this graph may be misleading in one sense, in the sense that in order to make the graphs small, we aggregated false positive and false negative. So the incorrect bar contains all false results, false counterexamples and false proofs of safety. And the correct is also correct counterexample and correct proof of safety. So that's one thing. This is hidden. You don't have this information, so you cannot discriminate. Since I spent some time actually reading through the raw results, the mathematical library, yes, causes false counterexamples, but we were also triggering a lot of bugs where the verifier will just guess true for a whole thing. Second consideration on that, only the first 3 subcategories contain call to the mathematical library. The other 3, which actually dominate the number of things, they are neural networks that are fully based on the ReLU function, so it's only multiplication, additions, and if statements. That's it. So you don't have this problem of semantics. My experience running with, working with the SBMC on neural network code is that there's not much this sort of massive floating point C codes in the usual regression tests of the software verifier. So sometimes, like in the past, we found bugs, like for example, SBMC was not handling correctly vectors, so arrays with more than 2 dimensions. Neural networks, the first thing they do, they declare a massive tables of parameters. For each layer, it's a matrix, so you have 3 dimensions. And this was never tested before. And so there was a quick fix. But if you're not part of the development team of a software verifier, if you can only use it off the shelf, you're liable to this.
So just to summarize, if I understood correctly, so you had both the scenario where you had false positives, which were to be expected because of this difference in semantics, but you also uncovered actual soundness bugs in these tools when they were saying things were safe when they're not.
Yes.
I see. Thanks.
Yeah.
Can I just add something? I looked into these benchmarks somehow, not very deeply. And what I found is because we increased the precision, so instead of, I would call the benchmark we call cosine, and we just return, this can be anything from -1 to 1. Right? But now cosine, when we implemented it, is this massive floating point implementation of multiplication, divisions, and whatever. And because now the software has to go through all of those, all the formula, it actually is lower than if we just bound the result of the first time. So
you do have the result that if you make the solver do things correctly, it will be harder.
Yeah. So we also dropped the number of correct results because now we are being more precise, and we don't actually need it to be, but now we are more precise.
And there are soundness issues, right? So it was necessary to be. So I remember during my PhD, once I had this great quote, I showed it to my advisor. The first thing he asked me, "Are you sure you're sound?" And then I wasn't. And then the quote got much worse.
And it's very interesting to hear about multi-dimensional arrays because this is my approach. Okay, so I implemented that in SBMC during my PhD, and one of the problems there is that I wanted to. So arrays in SMT are expensive, right? Because for every update you do, you create a new copy of the whole array. And in order to keep the memory lower, for multi-dimensional arrays, I would just get the lowest number of bits to represent it and just multiply the indexes everywhere. So whenever we have multi-dimensional arrays, we are slower because we are doing multiplications in SMT. We can be faster if we, instead of just multiplication, we just do shifts and just using more bits to represent the multi-dimensional arrays. But that's a trade-off. We have in SBConf, for instance, we have a threshold of 15 gigabytes of RAM. So a lot of the decisions on the SBMC are were guided toward this limits of memory and time. So in the case of multi-dimensional arrays, we can be faster, but then we use more memory. So that's a trade-off that we need PhD students to investigate for us, right?
We were talking about soundness, and for me, it's like if we increase the precision, maybe, or if you're using another approximation before, I would expect it more false negatives because you have more counterexamples, right? But I would expect you to sound a huge alarm for the community for false positives because you were verifying a piece of code that is buggy, but you are reporting that it's safe when it's not. So I think mapping false positives, and especially when you connect that to the fact that we are using over approximations in the library doesn't make a lot of sense because we expect it to be more false negatives instead. So do you expect that? Do you get any pushback from that?
So we expect a lot of pushback because like something like that, when we submitted to SVComp, we thought, okay, the auto tools will run on the tool. We'll see a lot of incorrects. They will get angry at us. And then they will say, oh, there's more, we need more time. They actually didn't. So it's like kudos to the community. Everybody was quite excited about this, and they fixed it. Like without saying anything, the autos fix it. I think that it's literally a problem of the neural network code looks different than regular code, whatever regular means. It's a bit philosophy, but so you have these massive arrays full of parameters that take like two-thirds of the code is just a massive global table of parameters for the neural network. And then the actual code that is running is like these nested loops run in the matrix multiplication. And just in SVComp, the code does not look like that. Like a Linux kernel, a sorting algorithm, they don't look like that. And so the people doing software verify over the decades have added a lot of tricks to skip things, to simplify, to stop verifying the loop early if some condition happens. As soon as there is a tiny bug because they never thought of a corner case, that's gonna just break everything in the neural network. If you, for some reason, you stop early, like neural network code, you always execute everything because it's how neural network is done.
I mean, it's expected because you are dealing with the two most difficult problems in verification: loops and multiplication and division with time. But then, like, floating points. So
all of these in floating point. That's the thing.
I really expected that the two, as you said, like they will still be sound. You know, like if you don't know the answer, just abort or unknown, rather than this false positive. So I think you should really use that data to sound an alarm.
Yeah, but again, what I was saying is that they are not unsound because the mathematical techniques they are using are unsound. They are unsound because there is bugs. Because over the decades of development, there's never been a piece of code that looked like that, and so the programmer never thought about that. So it's all thing that you just need to get the authors, like once the benchmark is done, the authors will look at it and they'll be like, oh God, I should have fixed this earlier, I never realized. And so that's why I think all these tools have been able to fix things in the span of a couple of weeks. If there was something wrong with the mathematical technique they were using, they would not have been able to do this.
Yeah, I think also floating points are a big problem there because you cannot find a ground truth for that. You just can't. Like the state space is too big. How are you going to check that every single operation of the floating points are correct? And if you look at, like a few years ago, they found a bug on Intel processors that when you call sign with some weird floating point, it will just return a wrong value. So it's really wrong, right? Out of precision. So it's really hard to develop a backend in our case for floating point where we can code operations and we compare against, I don't know, Muzzle, libc, or glibc, and we get different results because the way that the code that were implemented are slightly different, and then when we encode them symbolic, we get those small differences in the result, and it's really hard to tell which one is correct. So not having a ground truth is really, really hard when dealing with floating points.
But on that, doesn't the community agree on the IEEE 754 standard? Well, I don't mean in implementation. I mean in what would be correct.
So, IEEE 74 standard. The last standard only mandates bit-precise behavior for some parts of floating point. Well, bit-precise behavior will be like, imagine the input is actually infinite precision, do the operation, and then round afterwards. So if I remember correctly, this is addition, multiplication, square root, a few things like that. But yeah, FMA, fuse, multiply, add. But for the rest, so the cosine, the exponential, the logarithm, this is a recommendation. Which means, you know, if you run on a GPU and to save chip space, the hardware engineer decided my cosine implementation will be more or less, you cannot really complain, right? Because they are following the standard. But the problem is if you then have, for my case, if you have a data scientist that writes a neural network with a cosine inside it, the data scientist is expecting this operation to actually be bit precise. And then you deploy on a platform that is not, the behavior will change, and you will not be aware of this. So that's, see the problem. You're like building on shifting sand.
Yeah, sorry, just one last question. Have you tried to run that on real arithmetics and see what comes out the other way? When we code the SMT, you just use real arithmetic with infinite precision.
So this is something we have not done, and it was something we were thinking about as a way to speed up things.
Speed up?
Yeah, because as I said, like the reason why most of the mainstream verification approaches for neural networks are in infinite precision is that in infinite precision you can afford doing a lot of tricks in absolute interpretation, zonotopes, polytopes, propagate things. In floating point, each one of these things, or you need to be careful, is my approximation error blowing up and things like that. So we were thinking, okay, can we do, at least, if not using the SMT solver, at least do some absolute interpretation in infinite precision, and then somehow use these as invariants, plug them back into the C code. This is all future work, and this is all unexplored, basically. It's literally unexplored territory. So
that would be very interesting to see the trade-off, because when you're dealing with floating points in SMT, some SMT solvers, they generate very optimized code for the processor. Like they generate floating point operation for the processor that's very fast. But when you're dealing with real arithmetic, you just can't. Right? You have to have your own algorithms to solve this stuff. So if you can simplify the formula, not the formula, the program, using real arithmetic, assuming real arithmetic, that would be a nice, interesting comparison to do.
It's, but as I said, it's all future work, so something we will do in 2024, but something we also hope other people will do, because again,
Oh, Rafael is the PhD student.
Good. Yeah, so it's lunchtime, right? So we're gonna return 2 p.m. with the tutorial, okay? So I hope you have enjoyed it, this session, the morning session.
Thank you.
And then we look forward to meeting in the afternoon. Okay, Edja, the location, because it's gonna be a lab, a computer lab, right? Yeah.